How do we collect gases in the lab? A lot of students think that you would use balloons and attach a balloon to a test tube or to some other glassware and then capture the gas in the balloon. The problem is that sometimes our glassware gets hot, and so we need some sort of way to still capture that gas without melting the balloon. And the solution to this is to bubble the gas through water and to collect the gas through water displacement. So in this picture down here at the bottom, we have a column of water. It's filled all the way to the top. And then when we do our chemical reaction, we have a tube, either glass or a rubber tube that's connected to where our reaction vessel is, and we can bubble the gas through the water, and then the water will trap that gas. And we actually can read the volume on the glassware, and we can measure exactly how many milliliters of gas that we collected. And that is how we determine the volume of that gas. There's a problem with this, however, and that is that not only do I have the gas trapped right above the water, but some of my water vaporizes. So I will not only have my gas particles, but I will also have my water particles that are in there too. When it's mixed with the water, it is known as a wet gas. Well, we can take the water out of the gas through a physical mean by passing the gas over a chemical that absorbs water vapor, or we can mathematically get rid of the gas. And that's how it's easiest to calculate the pressure of that dry gas. So now we come to Dalton's law of partial pressure. And Dalton, he was the man that came up with the atomic theory of matter, how everything is composed of atoms. And his law of partial pressure says that the total pressure is equal to the pressure of one of the gases in the mixture plus the pressure of the next gas in the mixture. And if there's more, you would just keep going. So you add up the partial pressures of each of the gases in the mixture, and then that will give you the total pressure. So let's look at the picture here. So we have our gas 1 in a certain volume of container, and then we also have gas 2 in a certain volume of container, and it has a certain pressure. They both do have their own pressures. If I combine the gases, then I get this additive partial pressure. So the pressure of the first gas plus the pressure of the second gas, they will add up and give me my total pressure. And this works for any number of gases. So not just 2 gases. If you have 3 or 4 or 5, you would just add up each of their individual pressures, and then that would give you the total pressure. So this is Dalton's law of partial pressure. And on these problems, when you're doing them, don't overthink them. So here's another problem that we can look at. So down here we have these vessels. So we have our first vessel has a pressure of 200, our second 500, and 400. And so what is the total pressure if I were to take all 3 of these gases and put them together in the same volume container? Well, you would just add up their pressure. So 2 plus 5 plus 4 is 11. So this is 1100 kilopascals would be the pressure when they're all combined in this vessel. Now, what if instead of not knowing the total pressure, what if I didn't know this second pressure? So I knew the pressure of the first gas and the pressure of the third gas, but not the pressure of the second gas. Well, you would just take your 1100 total pressure and subtract 200 and subtract 400, and then that would give you that pressure of that second gas. So in the gas that we collect over water, that wet gas is contaminated with water. So all I need to do is I need to look on a water vapor pressure table and look up using the temperature of the gas or of the water. They should be the same because they're touching each other. So we can look up that partial pressure of the gas. So let's look at this problem. So we have some gases collect over water at 22 degrees Celsius, and I have a total pressure of 85.4, and we're going to relate this to Dalton's law of partial pressure, so I'm going to call that my total pressure. And it says, what is the pressure of the dry methane gas? So that's what I want to find. So the pressure of my methane. And I can look up on my water vapor pressure table using the temperature of 22 degrees Celsius, and I find that the water exerts a pressure of 2.6 kilopascals. So this is the pressure of the water. So all in all, I have my total pressure is equal to the pressure of the methane plus the pressure of the water. So we gathered that methane over water. And I can look up what the water vapor pressure is by just using that table, and then I'm told the total pressure. And so to find out the pressure of my methane gas, I just take the total pressure and I subtract that water vapor pressure. So we have 85.4 minus 2.6. And we get 82.8 kilopascals. So this is the pressure of the dry gas. So that's kind of another clue to remind yourself to get rid of the water vapor. And just do it mathematically. Look up in your homework, you should have a water vapor pressure table chart. And you just use the temperature and look up what the pressure of the water is at each of the different temperatures. So it should be question number 43 or one close to it. So we have a 450 milliliter sample of hydrogen this time is collected over water, and it's at 12 degrees, so a little bit colder than what we had in that last problem. The pressure of the hydrogen and water vapor mixture is 78.5 kilopascals, and we need to use the water vapor pressure chart to figure out what the pressure of the water is. So my total pressure is 78.5. And I'm going to subtract the pressure of the water. So I look it up, and it's 1.4. So when I subtract this, I get 77.1 kilopascals. So that's the pressure of my dry gas. So that's another little clue that you got to get rid of the water so it can be dry. All right. And in part B, we are going to take what we found in the lab and we're going to change it to standard conditions. So standard temperature and standard pressure. So standard temperature, or our second situation, our T2, is going to be 273 Kelvin. And then our standard pressure, or our P2, that is going to be 101.3 kilopascals. So because the total pressure of our gas was measured in kilopascals, and also that water vapor pressure chart is also in kilopascals. So we want our standard pressure to be in kilopascals. So just so it matches. All right, and let's look at the problem. So we have our V1 right here. So that's our starting volume. We have our T1 right here. So the 12 degrees Celsius. So we need to change that to Kelvin. So plus 273, and I get 285 Kelvin. So this is my T1, 285. And then I have my P1, which is the dry gas. I don't want to use the total gas anymore because I want to not use the mixture. I want to use just the hydrogen. Okay. All right. So I think I have everything. I have V1, I have T1, I have P1. So notice I have temperature, pressure, and volume that are involved here. So I need to use the combined gas law. So P1 times V1 over T1 equals P2 times V2 over T2. And it says, what is the volume? So that's what I need to find, my V2. So I want to solve for my V2, so I'm going to multiply by T2 and divide by P2. And what I do to one side, I have to do to the other. So this is going to cancel, and I'm going to be left with V2 is equal to this combined gas law, just rearranged. All right, so let's plug in all these values in here. I didn't leave myself much room. I'm just going to have to write really small. Let's cancel our units. So Kelvin cancels. We have kilopascals canceling, and our answer is going to be in milliliters. And for my answer, I get 328 milliliters. So I have 3 sig figs, and I believe on this slide there's actually a decimal right there. So let me just put that there. So we have 3 sig figs, and make sure that when you're doing your math that you multiply everything on the first line, and then if you keep those numbers separate when you put them in your calculator, the ones in the denominator, make sure you press the divided sign first. So it's all those numbers multiplied on the top, divided by 101.3, divided by 285. And all your units cancel out to leave you with milliliters, 238 milliliters.